This is Colin Selleck of Binghamton University. This video lecture is for the course ME273 Statics, and we use the book Statics by R.C. Hibbeler. Today I'll be talking about simplification of a force and couple system and further simplification of a force and couple system. That's chapters 4.7 and 4.8. After today, you will be able to determine the effect of moving a force and find an equivalent force couple system for a system of forces and couples. So we'll look at some applications. We'll define equivalent systems and system reduction. We'll look at some techniques to do that, and then we'll solve some problems. First, some applications. Here you can see 4 different instances of a force being applied to this stick. And what are the differences between those? And why do we want to know? We need to know because we're going to be designing load-bearing structures, so we need to be able to analyze all of these different cases. Now here you can see several forces and several couples acting on this I-beam. Now for the purpose of designing the I-beam, it would be very helpful if we can resolve all these forces into one single force and all the couples into one single couple. It would greatly simplify the analysis if we could do that. So sometimes it's convenient, like I just said, to reduce a system of forces and couples just to a simpler form by replacing it with an equivalent system, it's called. And that would consist of one resultant force acting at some point and a resultant couple moment. A system is equivalent if the external effects it produces on a body are the same as those caused by the original force and couple systems. The external effects of a system refer to translating and rotating motion of the body is free to move, or refers to the reactive forces at the supports if the body is held fixed. So if I hold a stick in this fashion and there's a force at the end of the stick, I can also put in a force minus F and plus F at the hand, and if you sum the forces here, you'll see that this F cancels with this F and we're left with this. So this is an equivalent system to this, and that demonstrates the principle of transmissibility, which states that a force acting on a body, the stick in this case, is a sliding vector, since it can be applied at any point along its line of action. But if we want to move a force off its line of action, as you can see in this vertical force here, we can attach a pair of equal but opposite forces at the hand, as you see here, and this force will cancel with this force, but we also have to include the moment due to this initial force, which was, right, F times D, right? So we have to include that. If we're going to move the force from here back to here, we have to also include the moment that resulted from the original configuration. A system of several forces and couple moments acting on a body can be reduced to one single resultant force acting on the body at point O and a resultant couple moment. So as you can see here, this force F1, that force can be moved to the origin, or point O rather, as you see here, as long as we include the moment that was due to that initial force, and that moment of course is R1 cross F1. So we can do that for all the forces on here, and you can see that we've moved F2 over to O, but we've included that moment that was due to F originally, R2 cross F2. And then this is a couple moment, and you remember that's a free vector. We can move it anywhere we want on the body, and we just did that here. So this is equivalent to, we can do all these cross products and sum them, and we can make it equivalent to this. So the resultant force is just the sum of all the forces, and the resultant moment about the point O is equal to the summation of the moments about O plus any couple, summation of any couple moments that might be applied to the body. Let's look at this little example here. The weights of these traffic lights can be replaced by their equivalent weights, which is, equivalent weight would be W1 plus W2, which you see here, and a couple moment, that moment R, about the point O. We can replace it with D1 times W1 plus D2 times W2. So in this case, we can make this this system's equivalent to this system. We moved the two weights to point O. We added them together to get the resultant weight. But when you move a force that's a distance not along its line of action, you also have to account for the moment that that force had. So we would also apply a moment at point O, which is equal to this in this case. Now we're going to move into chapter 4.8, which is further simplification of a force and couple system. So in that preceding section, we developed a way to reduce a force and couple moment system acting on a rigid body into an equivalent resulting force F sub r acting at some specific point O and a resultant couple moment. The force system can be further reduced to an equivalent single resultant force provided the lines of actions of Fr and M, the moment, are perpendicular to each other. So because of this condition, there's concurrent, coplanar, and parallel force systems can be simplified. So in this case, this is a concurrent force system. It's one in which the lines of action of all the forces intersect a point. So then the force system produces no moments about the point O. So as a result, the equivalent system is just F sub r is equal to the summation of all the forces. So concurrent force systems, all the lines of actions intersect at a single point, resulting in no moment. So in this case, the resultant vector is the summation of all those forces. Now in coplanar force systems, the lines of actions of all the forces lie in the same plane, but they don't intersect at a point. So the resultant force, F sub r, is equal to the summation of all the forces of this system. Furthermore, the moment of each force about any point O is directed perpendicular to this plane, right? So this is a 2D problem. We know that the moment vector direction is coming out of the page. The resultant moment can be replaced by moving the resultant force F a perpendicular or moment arm distance D away from the point O, such that F sub r produces the same moment about the point O as in the original case. This distance D can be determined from the scalar equation. The moments about r is equal to the resultant force times distance. This is a scalar equation here, which is equal to the summation of moments. Or D is equal to the resultant moment about point O divided by F sub r. You see what we did here? We sum forces about some point O, and we have the resultant force acting at that point O with an applied couple, applied moment rather, due to all these forces here. This is also equivalent to moving that resultant force vector some perpendicular distance away from D, such that Fr times D is equal to the original moment calculated in the original system. Now, parallel force systems, they consist of forces that are all parallel to the z-axis, as you see here. It can be parallel to any axis. I'm just saying all the forces are parallel to each other. Thus, it means that the resultant force F sub r is equal to the summation of forces. And we can apply that at point O, and that F sub r is parallel to this axis. The moment produced by each of the forces lies in the plane of the plate, right? So F sub r and the moment, the resultant moment, are mutually perpendicular, as you can see here. As a result, the force system can be further reduced to an equivalent single resultant force acting through the point P, as you see here. the distance d that we have here along that BB axis there would be d is equal to the summation of moments about O times d divided by, F sub r. So parallel force systems, all the forces are parallel. That means that we have one single resultant force is in this direction of the parallel axis. The moment due to that, of course, is going to be perpendicular to the force, and as you see here. And we can replace this system with this system. The resultant force is still the summation of all the forces, but now to account for this moment vector, we're going to move P some distance away from O, some perpendicular distance away from O. And we can calculate what D is. We did this earlier, similar thing, by taking the summation of the moments and dividing by the resultant force. So let's do some examples. Here we have a 2D problem. We've got a 200-pound force, 50-pound force, 100-pound force. Find the equivalent resultant force and couple moment acting at point A, and then the equivalent single force location measured from point A. So we're going to sum all the forces to find the resultant force. We're going to find and sum all the moments, and then we're going to shift F sub r to a distance d such that the moment will be the same as it was in the original problem. So let's sum forces in the x direction, and that is equal to, we have this 50-pound force here. It's positive x, and so that is 50 times the sine of 30. We've got this 100-pound force on a 3, 4, 5, and it's also positive. X component's also positive, so that would be plus 100 times 3/5. And that is equal to 85 pounds. Some forces in the y direction, and that is equal to the 200-pound force you see here, plus the y component of the 50-pound force, which is positive, so it's times 50 times cosine of 30. And then the component of the 100-pound force in the y direction, it's negative, so it's minus 100 times 4/5. And this equals 163.3 pounds. So the next thing to do is to sum moments. So the summation of moments is equal to, well, this 200-pound force tends to rotate counterclockwise, so it's positive, and we're summing moments about point A. So that's 200 times 3. And the 50-pound force, only the y component produces a moment about point A, and it is a total of 9 feet away, and it wants to go counterclockwise as well, so it's also positive. So it's plus 50 cosine of 30, that's the y component, times 9. And the last force is this 100-pound force. The only moment it creates is due to its y component, and it tends to rotate clockwise, so this one's negative, so this will be minus 100 times 4/5 times 6 feet. So that resultant moment comes out to be 509.7 pound-feet. It's positive, so it's counterclockwise. So that results in, the resultant force acting here with some moment. We want to change that. We want to move F sub r away from A, but maintain the same moment. And so F sub r, if you look at it here, the only component of F sub r that produces a moment is the y component, right? The x component passes through A, so it doesn't produce a moment about A. So the only component of the resultant force that produces a moment is the vertical component. So the moment about A, which is 509.7, is equal to the y component of the resultant force, right, which is 163.3 pounds, times this distance d. That's times d. We solve for D. D is equal to 3.12 feet. So what I've done is I've taken all those forces and I reduced them to one single force, F sub r, acting at some distance away from point D. There are no, in this case, the resultant moment is 0. We just replaced everything with one single force acting at some point. Makes analysis so much easier when you can do this. So we have this slab here, it's subjected to 3 parallel forces. Find the equivalent resultant force and couple moment about the origin O, and find the location, now that would be an XY location, of the single equivalent resultant force. So then first we're going to find the summation of forces, then we're going to sum moments, and it is going to end up, we're going to have moments in 2 different directions here. This is a 3D problem. And then find the location of the single equivalent resultant force by using these 2 equations here. So the resultant force is equal to, we have a 100 positive K, we have minus 500 in K, and we have minus 400 in K. So the resultant force is minus 800 K newtons. Now we're going to sum moments. So the resultant moment about point O is equal to, now I'm going to use the vector form. So moment is equal to R cross F to solve this problem. So let's take the 100 Newton force first, and its R vectors from O to that force, so it's 3I. So 3I cross with 100 K. Now let's take the 500 Newton force, which is here. Its R vectors from the origin to there, and so its unit vector, its position vector rather, is 4I plus 4J. 4I plus 4J. And that's crossed with the force, which is minus 500K. And lastly, we have the 400 Newton force. Its R vector is along the y direction, and it's equal to 4 meters. So that will be plus 4J crossed with minus 400K. Now here's where you need to do those cross products on your own. And in one of the past lectures, I showed you that little mnemonic for doing that. And I use this one, IJ, K, IJ. So let's evaluate all these cross products. So I cross K is minus J. So this would be minus 300 in J. I cross K, this I cross this K, is also minus J. So we have 4 times minus 500 times a minus 1. So that would be plus 2,000 in the J direction. Now we have J cross K. J cross K is I, and it's 4 times minus 500, so this would be minus 2,000 in the I direction. And lastly, we have this one, which would be J cross K, which is I, and it'd be 4 times minus 400, so it's minus 1,600 in the I direction. And when you simplify that, these are the moments about point O. You get minus 3,600 I plus 1,700 J Newton meters. So we have the resultant force, and now it's going to be applied somewhere in the middle of that plate, right? Some distance x and y. So this would be some distance x and some distance y. We want to know what those are. So let's look at the x direction first. X, the only part of the moment that applies here is the y component of the moment, or 1,700. This resultant force times that distance x is going to give me a moment about the y-axis. That's why we do that. So it is equal to 1,700 divided by the summation of forces, which is 800. and that would be, it's actually minus signs in both of those. That's 2.13 meters. Now in the y direction is this guy right here, and it's that y direction times resultant force is going to tend to produce a moment about the x-axis, so we only need the x component of the moment vector, so that would be minus 3600 over minus 800, and that's 4.5 meters. So here we have a 2D force and couple system as shown. We have 3 applied forces and we have an applied moment. Find the equivalent resultant force and couple moments acting at this point A. So we're going to sum all the forces to find the resultant force, and then we're going to find and sum all the moments resulting from moving each force to A, and then add that to the 1500 Newton meter free moment to find the resultant moment. So some forces in the x direction, and that is equal to, this one is 450 times cosine of 60, and it's positive. 300 Newton doesn't contribute. 700 Newton is going in the minus x direction, so 700 times sine of 30. And that equals minus 125 newtons. There's some forces in the y direction. In this case it's 450, this is negative 450 times the sine of 60, minus 300, and minus 700 times cosine of 30. And when you do all that, it comes out to be minus 1296 newtons. So if I ask you to find the magnitude and the direction, you know how to do that. You take the square root of the sum of squares of these two, and the direction would be the inverse tangent of the y component divided by the x component. I think we've done that before, but we can do it again. So the resultant force is, the magnitude of it is the square root of minus 125 squared plus minus 1296 squared. And that equals 1302 newtons. And the angle at which it acts, it's they're both negative, so we're in the third quadrant here, right? And this is fx, and this is fy, and this is theta. So theta is the inverse tangent of fy over fx, or minus 1296 over 125. And that equals 84.5 degrees. Now let's sum the moments about point A. And the 450 Newton force, it just, only the y component contributes to the moment, and it's going clockwise, so it's negative, so it's minus 450 sine of 60 times the moment arm, which is 2 meters. The 300 Newton force is all vertical, and it is 2 plus 4, it's 6 meters away, so it's plus 300 times 6. I'm sorry, both of these tend to go clockwise, so they're both negative. This is minus. And lastly, we have this 700 Newton, only the y component contributes, and it's going clockwise as well, so that's minus 700 times the length of the beam, which looks like it's 9. Actually, 700 times cosine 30 times 9. And lastly, we have the 1500 Newton meter couple. It's clockwise, so it's also negative, so minus 1500. And when you do all that, it comes out to be minus 9535 Newton meters, so it's clockwise. So let's do another problem. We have these forces and a couple moments applied to the pipe. We've got a 200 Newton force, 100 Newton force, 300 Newton, and a couple of couples. So our plan is to sum all the forces. What we want to find is an equivalent resulting force and couple moment at point O. So we're going to sum all the forces and sum all the moments using this equation. So this is the sum of all the couple moments, the 180 and the 100, and these are the moments due to the forces. So I'm going to do this in vector notation, so I need all the forces in Cartesian form. So F1 is 300, and it's all in the k direction, 300 k newtons. F2 is equal to, F2 is here. Now F2 is pointing down 45 degrees from the xy plane. It has no y component. Its x component is positive, and it's 200 times cosine 45. That's in the I. And in the z direction, it's minus 200 sine of 45 in the k direction. And that's in newtons. And that comes out to be 141.4 I minus 141.4 k newtons. F3 is just pointing along the y-axis, so F3 is equal to positive 100 J. And now we need our R vectors, because we're going to calculate the moments used in cross products. So for force 1, R vector R1 is from O to A, so it's 0.5 I. R2, likewise, is also in the I direction, and it's 0.5 plus 0.6, or 1.1 in the I, and R3 is equal to the total length of everything, 0.8 plus 0.6 plus 0.5, which is 1.9 in the I. And all of those are in meters. We've got a couple of free couple moments here. We have to write those down too. So MC1 as a vector, it's all pointing in the z direction, so it's 100k Newton meters. Now this moment is applied at 45 degrees down from the xy plane, so the moment of 2 as a Cartesian vector is equal to 180 its magnitude times, now in the I direction it's positive, and it's cosine of 45 in the I, and the z direction it's negative, so it's minus sine of 45 in the j. And this comes out to be 127.3 I minus 127.3 k Newton meters. So the resultant force is just the sum of all the forces. You know, it's F1 plus F2 plus F3. And when you do all that, the resultant force comes out to be 141 I plus 100 J plus 159k newtons. Now the resultant moment about the point O is equal to the summation of all the couple moments plus the summation of all the R sub i's crossed with F sub i's. Now this I is an index on the summation, it's not a unit vector. So this would be equal to the couple moment summation. So for one, we did this in the previous page, so it's 100 in the K plus 127.3 in the I minus 127.3 in the K. Now that's this first term. That's the sum of all the couple moments. And now we need to add into that. I'm going to come over here and do our little matrices I, J, K. R1 was 0.50, and force 1 was 0.0300. Plus, again, I, J, K. And R2 is equal to 1.1, and F2 is equal to 141.40 minus 141.4. Plus the last force, I, J, K. R3 was 0.9 J, 1.9 and 0, and that F3 was all in the J direction, 100. So when you do all that, you take this plus this minus that plus this plus this plus this. You do the determinant method here. I'm not going to do it here, but the answer is summation. The moment about O, the resultant moment about O is 122I minus 183K. And that would be Newton meters. This concludes the lecture on section 4.7 and 4.8, where we simplified force and couple systems. The next video is on chapter 4.9, reduction of a simple distributed loading. See you in cyberspace.